It gives me great pleasure in welcoming Johan Paduart. Within Energy Impact's long-term market modeling team, Johan leads the outlook on Iberia and Brazil. Johan also mentors junior analysts, drives innovative solutions, and ensures the implementation of robust workflows. His experience includes over 20 investment appraisal studies for ENGIE climate risk analysis and decarbonization pathway studies, showcasing his expertise in advanced modeling, investment appraisal, and risk assessment. Can you put your hands together and welcome Johan to the stage?
Good afternoon. Thanks, everyone. So this is work that was done in collaboration with my former colleague, in the meantime, Louis Gaïna. Maybe a quick intro on ENGIE. ENGIE is a French multinational, and we are present around the globe. We are moving away from carbon-emitting generation, and renewables are really at the heart of our strategy. Today, we have a portfolio of more than 50 gigawatts worldwide, and we are aiming at 95 gigawatts of mostly renewable capacity by 2030, and that sets a bit the scene for this presentation. So first of all, let me introduce to you the hydro portfolio that we will be looking at, and look at those beautiful pictures. Those are run-of-river and pumped storage assets that are located in the north of Portugal. We acquired them in a French consortium in 2020. And as you can see, well, it's generating over 3 terawatt hours of carbon-free electricity per year. There are 3 hydro run-of-river assets that are generating approximately 900 gigawatt hours per year. Those are run-of-river assets, but they do provide some flexibility because they have some pondage, and so they can modulate their production within the day. We also have 3 pumped storage assets. Well, actually, those are mixed systems, so they receive some inflows, which mostly during the wet time of the year will lead to a power generation profile that is close to run-of-river, whereas in the dry season, they will mostly be acting as a pumped storage. Now, the question that we want to answer with this study is, well, can we combine those assets? Can we co-locate them with additional renewable energy sources, namely solar PV and wind? And what would be the losses that are incurred by our existing hydro portfolio? So a quick overview of the presentation. So I've introduced to you the hydro portfolio. I will quickly explain the asset valuation framework that we are normally using. We'll have a quick glance at the outlook on the Iberian power system over the next decades. Then I will explain how we've modeled the hydro assets with PLEXOS. I will give an outlook on the capture rate of the hydro assets and how the hourly dispatch looks like. And then we'll look into the different hybrid configurations that we have assessed and some numerical results. So first of all, the asset valuation framework, which looks as follows. We've seen this afternoon a couple of presentations on how a long-term power market model looks like, that you can have different market scenarios where you try to capture the different fundamentals and the different outlooks and the uncertainty there can be on the long term with respect to power demand, fuel, but also renewable penetration, the costs of batteries, and so on. So this is the first step, and this allows us to simulate power prices at hourly granularity. Now we here use a full-blown unit commitment model that covers 15 European countries, and we also account for different climate profiles. We integrate different climate years for demand, PV, wind, and hydro, and this then covers some of the volatility that we normally see on power markets. And it also ensures that we cover all spatial and temporal correlations that there exist between different risk factors, and this can be within a given country, but obviously this also works on a European scale, meaning that if you have a period of Dunkelflaute, it would appear in your Belgian, French, and German prices. So this is the starting point, and we end up with those hourly prices that we compute for a number of target years that cover 2025 until 2050. But then we simulate 11 individual climate years, and this is something also that we'll use later on to look also at the uncertainty of the outcome. Now, this is where we disentangle the complexity of our power system model and then the asset model. So we then have a dedicated model, which can be, in this case, for a hydro portfolio, but actually the principle also applies to, let's say, a CCGT or a battery or any renewable portfolio. And there we are going to have a more precise and detailed modeling of the assets at stake. And the advantage is obviously that you don't need to run the full-blown power system model to look into sensitivities. Obviously, it's very important to be consistent between the power system model and the dispatch model. When it comes to renewables, it means that you need to replay the same weather years to ensure that you respect those spatial and temporal correlations. When it comes, for instance, to thermal assets like a CCGT, then obviously you need to make sure you use the same fuel and CO2 prices, otherwise you will get inconsistent results. So here specifically for the hydro, it's really important to couple the power system model and the asset model and to use exactly the same hydro years, given that there is this phenomenon that we call the natural hedge, the hydro in Iberia. When you have low hydro years, prices are typically higher and vice versa. Then we have a bit of post-processing on the results coming out of PLEXOS, and from the weighted average over the different climate years, we can obtain the revenues for the assets that we're looking into. Then a quick glance at the Iberian power mix over the next decades. Without diving too much into the details, because this is really a separate exercise that was done earlier on. So we here have a view on the left-hand side of the capacity mix in Iberia and the generation mix on the right-hand side. Obviously, the increase of power generation capacity and generation mix reflects the fact that we have an increasing demand. Where does this come from? Well, obviously, there is the gradual electrification of transportation. There is also additional heating, so the heat pumps. We have data centers also in our assumptions. And very important also, a development in this particular macroeconomic scenario of the hydrogen economy. Now, the bulk of that demand is covered by PV and wind. And yeah, as you can see, this is going to be really the bulk of the generation mix on the right-hand side. What you can also see is that we are following the plans to phase out nuclear by 2035 in Spain. And what is also interesting to see is that the CCGTs shown in green here, they stay in the system until 2050, and the reason for that is that they are a firm capacity provider together with batteries. Now, on the right-hand side, you can see that the running hours are getting less and less, so there's less and less contribution in the generation mix, again, reflecting the fact that they are a capacity provider and not generating that much energy in the end. Now, looking closer into the hydro portfolio and how we managed it. So, yeah, for confidentiality reasons, I'm not showing too many details, but the topology can be seen on the right-hand side. We have a few run-of-river assets, and then we have also the setup with the pumped storages. We are using pretty standard properties here. So the run-of-river will be characterized by turbining capacity, the storage, the limited storage volume that there is, the efficiency of the different units per plant, and we also model the unavailability with a profile that is shown on the bottom right. Pretty much the same image for the mixed pumped storage. We also have here a pumping capacity, and on top of that, the round-trip efficiency that we also need to define to characterize the pumped storage action. Next slide. Yeah, so on top of that, we have a bit of peculiarity. So obviously, we are looking at the variability of hydro, which means that we are modeling this variable nature by looking at different weather years for the hydro. A picture of that can be seen on the bottom right, where you see the different inflows for the 3 rivers that are leading to the different assets, and part of that is heavy correlated. And we're looking here in this exercise at 11 weather years. Another specificity is that one of the pumped storage assets also provides strategic water reserve, which means that we need to remain within certain bounds, and some of the water cannot be used throughout some months of the year. On top of that, we have also an ecological flow that needs to be respected throughout the year. And the last constraint we need to deal with is that with a competitor, we have some pumping agreements from one of the river, and we also need to make sure that the dispatch is consistent with that. But all of that are constraints that you can easily model with PLEXOS, as we've done here. Okay, then let's look at the outcome, very high level, looking at the capture rate. What does the capture rate represent? It's the generation-weighted average price over the baseload price. So it gives an idea of the premium that you can capture with the hydro assets on top of the baseload price. As you can see, for all the hydro assets, and there are 6 lines there, for all of these assets, the premium is higher than 100%. Why? Well, you have this flexibility, you can move around, you can shift energy throughout the day, so it makes sense that you're able to capture a price that is higher than 100%. The pink one, the pink line is actually the hydro asset, the run-of-river asset that corresponds to the least flexibility. It's the hydro asset that has the smallest storage reservoir, whereas on the other side, the green one is the one with the biggest reservoir. So all of that makes sense. What does the dispatch look like in 2030? On the right-hand side, where there in black you can see the typical average profile of the power price in Portugal by 2030 throughout the day for the 24 hours. And then you can also observe in the blue line the average dispatch of one of the run-of-river assets. And so it's striking how the power price, which becomes lower and lower during the day, is also then reflected into the dispatch. All of that generation is being moved away from midday to the morning and the evening peak. And this is basically reflecting the power dynamics that we observe given our assumptions in the power system model. So let's now look into those hybrid configurations or co-location configurations that we are looking into. We are interested in combining the run-of-river assets with some predefined combinations of wind and PV. And we are going to add those and then see what is the impact on the dispatch and also on the profitability of those hydro assets. What is the consequence? Well, if you put those assets on the same injection point, well, they will be competing for injection capacity. And so, you basically need to also decide upon a rule or a dispatch rule in which order you are going to dispatch those assets. Now, for this particular example, we have decided to always give priority to the renewable assets that will be added, and then we measure the losses that are due to this co-location. We measure that for the hydro portfolio. This is the way our client wanted us to present the results. So the 5 configurations are as follows. The first one, there we basically take a run-of-river assets and we combine it with the same installed megawatts of PV. So imagine you have 440 megawatts of run-of-river. You will combine it with 440 megawatts of solar PV. And then with the other combinations, we actually lower the solar PV capacity and we add gradually a bit more wind. This is in purple. And then the last configuration there, we only add 30% of wind. So what is then the impact on the revenues for those run-of-river assets? On the left-hand side, this chart presents in relative terms the revenue losses for the existing hydro assets. Again, the yellow line, this is the first scenario, and the purple one is the last scenario, only hybridizing with wind. And as you can see, the losses due to this co-location are rather minor. So we have revenue losses that are smaller than 1%. And then you can see as we are adding more and more wind with the blue scenarios, we can see that the revenue losses become higher and higher. Now the right-hand side is maybe even more interesting because what we have done there is to quantify the revenue losses per megawatt hour of hybridization. So imagine we add some solar PV, we look at the impact, the losses, and we divide this by the megawatt hours that are injected by the new asset. And then it really stands out how efficient hybridization with solar PV is, because the cost expressed in euro per megawatt hour is the lowest for the hybridization with solar PV. So you can see that the yellow line represents the lowest loss. We have somewhere between 0.5 and 1 euro per megawatt hour loss. And when we then look at hybridizing solarly with wind, we can see that actually there the losses are much higher on a per megawatt hour basis. So hybridizing with wind is quite inefficient, with PV is much more efficient. And then basically by choosing other percentages, you can actually tune a bit, and you can tune this efficiency the way you like. But obviously PV is very efficient, wind is not. So obviously the question is, why does this hybridization with PV work so well? Well, then what we can do is to look at the dispatch on a monthly granularity and hourly granularity before and after co-locating the assets. On the left-hand side, at monthly granularity, there's not much happening. So the blue line, the blue surface area represents the hydro dispatch after hybridizing, and the dashed line is actually the one of the reference case before applying this hybridization. So you can basically see no difference. On the right-hand side, this is more interesting. You see that adding the PV will slightly distort the dispatch of the run-of-river asset. So it's slightly de-optimized, but as you can see, it's almost the same. And the reason for that is very simple. By 2030, there will be so much solar PV in the Iberian power system that naturally those hydro assets will always put within the limits of the flexibility, they will always put generation in the morning and the evening peak, and they will move away as much as possible the generation from the solar PV hours. So basically you have an asset that already moves away all of that generation from solar PV hours, which leaves quite a lot of room to add solar PV into the mix and into this portfolio. And this effect is something that is not so visible with wind. And the reason for that is that wind on a local basis is not necessarily correlated with the wind that you observe on a national or Iberian Peninsula basis, which is different for PV. There you really have a very high correlation across the country and even in Europe. So the conclusion, so we've been using PLEXOS for two aspects of the study. First of all, we use it to model the long-term power price dynamics. Then we cut the problem into halves. We have the first half where PLEXOS allows us to come to these hourly prices for different weather years across the horizon. And then after that, we can focus on this complexity of the hydro portfolio together with solar and wind. And we can perform multiple simulations, and we have a simulation that runs only in a few minutes instead of several hours. We have also shown, that integrating some wind and mostly PV with existing hydro shows great potential. And in Iberia, this is really important because it's difficult to get your hands on transmission capacity, and it's quite expensive. So it's really a scarce resource. So if you already have some generation assets in the Iberian Peninsula, this is really a game changer. We've observed that coupling the run-of-river with solar PV is very efficient, even with an extremely high degree of hybridization. So in the H1 scenario, we've combined 440 megawatts hydro with 440 megawatts AC PV. And the reason why this is possible is because there's an extremely high correlation between the local PV conditions and the ones that you observe on the scale of the peninsula. We've seen that with wind, the hybridization does not work that well, so you need to limit somehow the installed capacity. And then even then there can be a good business case to hybridize, to collocate wind with hydro. And that's it for me. So pleased to hear your questions. Thank you.
Thank you very much, Johan. That was extremely insightful. Floor, I'd like to open up the floor for questions. Anyone got a question? There we go.
Thank you, Johan. It's going to be a quick one. Do you consider the curtailment for wind and solar in your modeling?
Yeah, of course. And so there can actually be curtailment. And so in this particular case, since we're always giving priority to solar, PV, and wind, and it's matching exactly the injection capacity, what we see is that actually it's the water that is sometimes being spilled. And then obviously there can also be economic curtailment because of the prices being zero. Yeah. Yeah.
Hi, thanks for the presentation. Hussam from Barinka. I have a question on, so you were explaining about the collocation of solar or wind with runoff river, which runoff river is inflexible compared to pump storage or hydro reservoir. Did you do any study on these two? Because that would be actually interesting to...
You mean to look at inflexible hydro?
No, like looking at collocation of solar with pump storage or solar with reservoir, if you did a study on that.
It's not shown here, but we've actually also tested it with one of the pump storage assets, and obviously it also works pretty well because that asset is going to pump whenever power prices are low. So actually the insights would be pretty similar for pump storage. Yeah.
A few more questions? Anyone? Here we go.
Yeah, thanks for the presentation. Rutger van Houten from Tenet. I was just wondering, why do the revenues decrease of the hydro assets when you add solar? It's just because you're spilling water?
Yeah, exactly. So in the dispatch rules that we have set up, we prioritize the renewable, the new renewable, with respect to the hydro. So by definition, you're always going to de-optimize compared to the reference case. And that can be either moving away within the flexibility, moving that to less expensive hours, but it might also mean that you have more spilling, yeah. It's a combination of both.
Any more questions? Hands? Brilliant. Well, in that case, I'd like to thank you very much, Johan. Brilliant. Thanks for the presentation. And yeah, one last round of applause, please.